to kind of kick off the hands-on portion of this workshop, we've asked 4 of our topic leaders to put together tutorial videos about some area of neuromorphic engineering that we think is really integral to the current and future work that is kind of changing how things are being done in the field right now. And so those videos are going to be made available as tutorial videos on YouTube that you'll get links to from the document. You've all received an email and the Slack channel and whatnot. But we're going to ask each of those teams to give us a quick little pitch for why you should watch their tutorial video, what you can expect to find in it, and how it might help you participate in some of the challenges that we're going to be throwing down to the community over the span of the next month. So with that, I don't know if we have an order predetermined, so I'm going to put Terry Stewart on the spot and ask him to be our first tutorial pitcher.
Sure. Hi, everyone. I don't know really what I want to say. So I do a lot of work with, so my background is I want to be building models of cognition, of brains. I want to understand what neurons, how I can organize neurons to do different algorithms. And the tutorial that I'm putting together, that I have, is sort of an overview of a particular tool set that we've been using for 10 years now, called Nengo, which is meant to be a sort of a generic software package for, you can use it for defining neurons and connecting them together, but it's got a couple nice features like support for lots of different hardware. So the hope is you can define your model once and then deploy it on different pieces of hardware. Another interesting feature that it has is a sort of this high-level abstraction that you can use with it, called the neural engineering framework, which is meant to be sort of across at least a reasonably large set of neuron types. There's a class of algorithms that you can specify by just sort of describing the high-level behavior you want, and have it sort of, given whatever particular neurons you happen to have on the hardware you're running it on, what's the best way to connect those up. So we have some automated tools for giving you a slightly higher level of abstraction if you want it. And then there's also a graphical interactive user interface, so you can actually sort of, as you're initially building your model, you can sort of play with it and see what's happening. And so that's all sort of covered in the tutorial that should be now posted. We've used it for a variety of different hardware over the years here. I've been coming to Telluride since 2011. And I'm really excited about seeing various different projects people might do with it. So yeah, I think that's my pitch.
Great, thank you, Terry. And as a point of reference, we're expecting that everyone will watch these videos on their own time, whether later today or over the course of the next week. And then there will be a live Q&A and kind of discussion session that will occur. I believe Terry's is going to be on Wednesday at the conclusion of the morning talks, or evening, or wherever you might be in the world. And so stay tuned for that. Let's go next to Cornelia, who will be the leader of tomorrow's discussion section. Cornelia, are you online? Oh, you're muted at the moment, Cornelia.
I also have a few slides. Is it possible to share the screen?
Absolutely. Let me make sure you are okay. You should be able to share your screen now.
Okay, you see it? Can you see it? Okay, so this project, not it does.
Yeah, you don't see anything yet.
Ah.
You have to complete sharing, I think.
Okay, let me see.
There you go.
All right. So this project is about the early motion pathway. Maybe comes closest to what Terry said as the challenges in looking at sciences. So
for the record, we're seeing Word, not PowerPoint at the moment.
We're seeing your notes, not the PowerPoint.
Ah, okay.
You're sharing the wrong window, I think.
There we go.
Okay. Okay, so the early motion pathway, what is referred to in the neurosciences, is these areas where it starts from the parasol ganglion cells at the retina over the LGN and involves areas V1, V2, and then D, and then also higher. But it's mostly about these areas. That's also the name. And we have been looking in the vision as computer vision scientists long at what are these processes, and we know what is computed. These processes that every vision system that moves needs. It's about estimating image motion, it's about estimating 3D motion, your own and those of the objects, and it's also about getting scene structure, so moving and what is moving independently. And there's also from the motor system tracking and eye fixations involved. Also, there are many algorithms that are successful, currently known as algorithms in the SLAM paradigm. Those don't tell us much about what biology does with motion. So our plan is to open this box of processes by studying properties of computations employed by the human vision system. And the way we are going to do it is through using stimuli, psychophysics, and computational modeling and technology. So we will start by looking at illusions of motion. So here are 3 described that you also can find ideas what we think is involved. One is the ouch illusion on the left, where even when you move your eyes, you see the insect moving. The famous snake illusion, where you probably see the different parts rotating. And another illusion called the stepping feet illusion, where they are moving parallel, but you see this stepping effect. So you see a different segmentation than it is actually going on. So how do I imagine this to happen? That we will be doing neural network modeling and also classic and spiking networks, as well as classic computations. We will be looking at the properties of the network. So the idea being that under regular conditions for normal patterns, the system predicts correctly. But under these illusions, it should, similar like the human vision system, have errors. And the work will go both ways. So we start with some illusions, develop our theory, or I will also propose to start with, as you can see in the tutorial. And then on the basis of the theory, we will try to create variants to test the theory. Such illusions can also give us a tool into looking what is the estimation, is the human perception, what kind of estimators is it using? Is it really using least squares, for example? And the other thing interesting, we will be looking at event signals that are at the core of neuromorphic processing to understand also the role of the event signal in image motion analysis and in segmentation. And we hope that this will become an interdisciplinary project. And if you have skills and are interested in mathematics, computer science, engineering, biological modeling, psychophysics, or neuroscience, please join it. So thank you.
Great. Thank you, Cornelia.
Stop sharing, right? Or you can.
Yes. All right. So Cornelia's discussion session will be tomorrow at the conclusion of the morning lectures. The Thursday discussion session will be led by Emre Neftci, who is online now and can give us a little of an idea of the role of learning in neuromorphic.
Hello, everybody. So so I'm Emre Neftci. I'm a professor at UC Irvine, and I was also trained by some of the folks at the Institute of Neuroinformatics. And that session and the tutorial that we're posting are going to be about learning in neuromorphic hardware, neuroscience, and machine learning. And so the tutorial itself first is going to start with some classical models of learning, such as SCDP and Hebbian learning, but then focus on the machine learning viewpoint of learning. So recently, thanks to some recent advances in the community and also work in our lab, we were able to find ways of training spiking neural networks using the same methods actually that are commonly used in machine learning. And interestingly, just like neuromorphic engineering piggybacked the CMOS and the industry in order to build larger chips, we're at a stage where we can actually piggyback on the software and the hardware that's built for deep learning, for prototyping and testing large networks that can be candidates for implementation in neuromorphic hardware. So what the tutorial that I'll be posting is going to go over is how you can implement these spiking neural networks using the same tools as in machine learning and use the libraries for auto differentiation in order to train them. Interestingly, through a theoretical analysis, you can find out that what auto differentiation is effectively doing is and meaning by the means of some constraints, you can synthesize actually synaptic plasticity rules and test them. And this, where synaptic plasticity is different from machine learning, is a few points. But one of the interesting points is what Shichi mentioned, is that so when you're doing in-memory computing, when your compute and your memory are close to each other, you need to find ways of training, of learning where information, where your processes can use local information. And so we can show that some of these machine learning driven methods, along with some constraints, really correspond to synaptic plasticity rules that people have observed in neurobiology. And so the resulting is basically the tutorial will result in a script or a software that you can use to train very large spiking neural networks, up to easily 1 million spiking neurons even on a single GPU. And train it for some classical tasks, but also, for example, using inputs that you would get from a DVS camera. So this is it's a huge step that we've made, I think, in the last years, because we were able to piggyback on all these different theories and also develop it for the domain of neuromorphic engineering. And I think this follows pretty much also the ideas that Terry Sinowski was talking about. So instead of coming up with a spiking neural network with the thousands of parameters that we can just set from your intuition, let's just instead just put our inductive priors on what we know about the computation of the mechanisms and let the neural network figure itself out. And interestingly, what you find also is that because we're training with spikes, you can let the network actually figure out whether it needs more of a rate-based encoding or spike-based encoding, but still implemented using spikes and spiking neural networks. So tutorial is called event-based learning and surrogate gradient learning. And also, so the session that we'll have on Thursday will also have a related talk by the group of Wolfgang Maas, who found also related and slightly different methods for training spiking neural networks using gradient-based mechanisms. So I'm looking forward to see you there. And if you have the questions about the tutorial, feel free to reach out to me on Slack.
Fantastic. That sounds compelling, and I'm really looking forward to that conversation as well. And we have one more, which will be represented in Friday's discussion. And this one will be led by Tobi. I think probably everyone here might recognize there's been a undercurrent in a lot of the discussion today about how much of the excitement in the field is sensory as well as computational. And so Tobi is going to give us a few minutes on event-based sensing and how, kind of what differentiates it from the type of sensing that people might use in other machines. Tobi? Tobi, are you muted?
I'll be much less than a few minutes. Thanks for the update. Everybody should now be using this web view of the workshop information to get the Zoom link and stuff like that. Don't look at the Google Doc, please, because it's like overloading the Google Doc somehow. And now I've replaced in the last email that I sent, it's the web link. Some people was telling me it doesn't work, but actually if you click on this link, it does come back to the same page. So it must be the right link. I think Jesse was somebody asking me on Slack about that. And then from this link, you'll also come to another link, which is the recorded presentations. And that's another published web page now where we're going to post unlisted YouTube videos of the presentations, which the speakers are willing to share with the workshop participants. And so my tutorial, it's not directly related to any of the challenges, but it is about event cameras. This is something I'm also preparing for SCIRC, the European Solid State Circuits Conference. It's quite a technical tutorial, but it has 3 parts. The first part is kind of lightweight. It's a history of silicon retinas. You guys have heard something about that before, including Misha's retina, silicon sees a cat. The second part is about dynamic vision sensor event camera technology. It's a lot of stuff about the dynamic vision sensor pixel circuits, temperature, mismatch, all kinds of practical stuff, including recent industry developments and improvements of readout bandwidth from different companies. And the last part is a bit shorter, but it's about algorithms and applications of event cameras, like the RoboGoalie that I had so much fun building at Telluride. I still remember going to the hardware store and buying the paint sticks and the plastic crate to build the goal. It was a wonderful time then to build this simple thing because it was so easy to build. And the last thing I wanted to say about that was that on the webpage of the workshop, I've also posted a very nice other tutorial, which is from Davide Scaramuzza, presented at CVPR in 2020. It's about event cameras, opportunities, and the route ahead. It's much more directed towards computer vision people. So guys who are more interested in computer vision, not so much about the device technology, should have a look at that because Davide has done a good job on collecting together recent developments. So that's it from my side. Thank you.
Okay, great. And yeah, going forward throughout the course of this workshop, there will be a large number of people who have deep investment and expertise with event-based vision. And so if, typically one of the strengths of the workshop is that everyone brings their hardware to Telluride, and then we are, able to experiment and collaborate and work hand in hand. That'll obviously be a bit more difficult this summer, but we do have lots of data sets, lots of expertise, and so this will be a great opportunity for you to get some hands-on experience despite not having the hardware if you happen to be among the unlucky folks without. Okay, well, I think that wraps up the day 1 session. We're really excited by the response and the enthusiasm of the community. So many of you have reached out so far. I know we have hundreds of you in the Slack channels. I strongly encourage everyone here who hasn't signed up yet to get in on Slack. Despite the fact that the video sessions and tutorials might be over for today, feel free to use the Slack channels as an asynchronous means of introducing yourself, reaching out, making new friends and collaborators, because we're expecting a lot of that to come out of today's meetings. Cornelia, thanks for co-hosting today. Is there anything else that we want to add before we wrap up for the day?
I don't think so. I hope you enjoyed.
Great. Okay, well, in that case, we'll speak to everyone on Slack. We're thrilled to have you all with us this year and looking forward to big things ahead. Take care, everyone.
Bye. See you tomorrow. Come and hear about learning and dynamical systems control. That's like a cutting edge of machine learning and control. They're finally coming together. The old-time control people are finally coming together with machine learning, and it's all happening right now in the last couple of years. Okay, see you tomorrow.
Great. Take care.
Thank you. Bye.